Hey kids, Smath here. So this video I want to talk to you about cell EMF, what it is, and calculating it in galvanic as well as non-galvanic cells. And so basically, let's start with a definition. EMF in this case stands for electromotive force. And what that really is just basically the conversion of electrons from a chemical source in our case. So we run a reaction, that reaction spits out electrons. Those electrons create an electromotive force. Your book talks about it being the sum. This is also another definition. This is the sum of the reactions at the anode and cathode. That's what these are. And so a couple things about these electromotive forces. The standard for this, and there's a chart of these. I believe I have it posted in Canvas. You can look them up on the web. They're just very simple to find. These are always written in terms of reduction. So in this case, we have two H pluses plus two electrons is going to make H2. This is called a standard hydrogen electrode. It has 0.00 volts. That's by definition what zero is. So remember, in a galvanic cell, we're looking for an E that is greater than zero. So simply put, positive voltage is galvanic. Another way of thinking about that is this is going to be spontaneous. It's going to give off that energy in the form of voltage. When you and then a lot of the same terms apply. Reverse a reduction potential. We're going to reverse the sign. If you multiply, now this one is weird. If we multiply a potential, and why would we do that? Why would we multiply a potential? To get our electrons equal. If you multiply a potential, do not multiply a voltage. Never adjust a voltage. All you can do is flip it positive or negative. Multiply a potential, do not change the E value. Well, then how does that work? How are we going to be able to make that happen? Well, here's what happens with that. When you double that sign, what's going to happen is that side of the cell is going to go twice as fast as the other side of the cell. So if this side generates two electrons once and this one only generates one, this one's going to go twice every time this one goes once. It's a relative rate. The last thing I have for these standard potentials is the more positive value, the reduction potential. This is going to sound weird till we do it. The more likely to remain as a reduction. So we have a couple problems for you here, and you'll see as we work through them. These first ones are simply use the standard values E standard cells to calculate the EMF and determine if they're galvanic. Remember, galvanic is just positive. That's all we're looking for here, kids. So positive cells. So we're given a couple of reactions. First one we're given is Cu 2 plus 2 Ags goes to Cu plus Ag2 plus. This is one of those cases where we're just using net ionics. Why did we have to learn net ionics? They were the most impossible thing. They destroyed my grade second quarter, first quarter. I hated them. They don't make any sense. Well, here's where we need net ionics. We only need to know the species that are changing. So we have a bunch of nitrates that are floating around in this cell, and we're not worried about those. They're not creating any electrical potential, nor are they useful to us. So what we do know, we've got to pull apart the two half reactions. Cu2 plus 2 electrons goes to Cu. And we have 2Ag goes to 2Ag plus. Hang on, I'm fixing. I know you guys were already ahead of me on that. 2Ag plus 1s plus 2 electrons. So here's one where we had to double that second reaction. No problem. So we have these for electrical potentials. The copper is going to be running at a positive 0.34, and the silver is going to be running at a negative 0.80. So if we add those two up, we get a negative 0.46 volts. That's the voltage, or E cell, and this is going to be non-galvanic. Let's look at our second one, B. Now we have Zn2 plus 4 OH minuses goes to Zn plus O2 plus 2 H2Os. Same rules apply. So let's pull apart our two half reactions. Now here's the thing, if you can't find the halves, they're written in the reduction potential tables, and you'll always have one of those. So you just need to find them. Here are the two that we have. We have whoops, excuse me. There's a 2 there and a 2 there. My apologies. And a 2 in front of the water. Okay, so we have 2 Zn2 plus 4 electrons gives me 2 Zns. And on the other side, we now have 4 OH minuses, breaks apart into O2 plus 2H2O plus 4 electrons. And I find my E standards. This is negative 0.76. This is negative 0.40. This becomes negative 1.16. Once again, non-galvanic. So we're not doing too well creating a galvanic cell, a spontaneous cell that's going to generate. What these two things are, these require energy. These are circuits that we've got to put energy in to make them go. So instead, what we could do is take this second one, we're going to make B galvanic. How do we do that? We're going to reverse the more negative. And so what we're going to do is reverse the top and make that 2 ZNs goes to 2 ZN2 plus 4 E's. Make this a positive 0.76 and keep the bottom the same. 4 OH minuses breaks apart into O2 plus 2 H2O plus 4 E's, and this is negative 0.40, which means I've got a positive 0.36 volts, and my overall equation is going to look like 2 zincs plus 4 O hydroxides is going to make 2 zinc 2 pluses plus O2 plus 2H2O plus 8 electrons. Now there's a bit of a problem with this, a huge problem with this. All of our electrons are on the product side. All we have is reduction and not oxidation. So we can't make B galvanic like that. You can't just flip-flop one. You've got a problem. This reaction is not going to be possible galvanically. Not for us. In the next video, we're going to talk about, given these two reactions, how do we make something galvanic? That's coming up next. I'm Smath. I hope this video helped you.